Here we have a geometric sequence. It's a geometric sequence because succeeding items are generated by multiplication rather than addition or subtraction, as was the case with arithmetic sequences. Now the multiplier here is 3 because 2 times 3 gives 6, 6 times 3 is 18, 18 times 3 is 54, and so on. Now this multiplier that's used to generate succeeding terms is called a common ratio. It's the common ratio in this geometric sequence. Now take a look at this pattern. If a sub 1 is 2, that's our first term here, a sub 2 is found by multiplying 2 times that common ratio 3. And then a sub 3 is the previous term times 3, and a sub 4 is the previous term times 3. You see, every time we generate another term, we're just popping in another factor of that common ratio. Now, more symbolically, we think of it like this. The second term has one common ratio. The third term has 2 factors of that common ratio. The fourth term has 3 factors of that common ratio. So we think of it like this. The first term has no factors of the common ratio. Second term has 1 factor of the common ratio, and so on. And so to generate the nth term, you see the expression for the nth term, it would be the first term times the common ratio used as a factor n minus 1 times. You see, we had the n minus 1 involved in the arithmetic sequences before, and now we see it again on our geometric sequences. Well, using this idea, we can generate an expression for the nth term, and we do that like this. Here's the geometric sequence we started with. We know that the first term is 2 and the common ratio is 3. And by the way, if you ever get confused about the value of the common ratio, and sometimes there is confusion because the terms are not as easily read, or you can't see through them as easily as you can here. They might be fractions, for example, and there might be a sign change between them. Well, under those circumstances, just realize that this common ratio can be found by just taking the ratio of succeeding terms like this. We could take 6 divided by 2 is 3. 18 divided by 6. 54 divided by 18. You see, it is a particular term divided by the one that precedes it that gives us this common ratio if we're ever confused about that. Okay, so the nth term is the first term times the common ratio used as a factor n minus 1 times. So here, the a sub 1 is 2. And the common ratio is 3, so it's 3 to the n minus 1. Here's the expression to generate the nth term. We could generate the 20th term, you see, just by replacing n with 20, and we would have the value of the 20th term. All right, let's consider a few problems. Suppose we want to find the 15th term if we know that the first term is 20 and the common ratio is 1.05. Well, we just start with the idea of the nth term. The nth term is the first term times the common ratio raised to the n minus 1 power. Oh, by the way, notice that in certain problems like this, you might see an expression and you might wonder whether or not it's geometric. You might think, well, is this a geometric sequence or an arithmetic sequence or something like that? And it turns out that when we see an expression in which we have a counting mechanism as the exponent on some base, it's the base of that exponent that turns out to be the common ratio. And we saw earlier with the arithmetic sequences that it was the coefficient of the counting mechanism that turned out to be important to us. That was our common difference. Okay, at any rate, let's see. The nth term is, and a sub 1, we're told, is 20. Common ratio is 1.05, and this is to the n minus 1. Now we're just plugging in the information given, but we're asked to find a sub 15. So a sub 15 is found by using our expression here and replacing n with 15. You see, and now we have 1.05 to the 14th. Clearly here we would use the calculator to make the calculation, but be careful in doing that. Don't start with the 20 in making the calculation. 20 is not raised to the 14th power. Only this factor, only the 1.05 is raised to the 14th power. So you might start right here in making the calculation. Punch in 1.05, hit the exponent key, then 14 equals, and then times 20. All right, and we find the value to be approximately 39.599. Here's another one. Now, this one involves fractions, and we may be told here, let's presume that we're told that it's a geometric sequence, and we want to find a particular item, a sub 8. Now, what's not clear here, perhaps, is the value for r, the common ratio. What are we multiplying by to get the succeeding terms here? Now, we can kind of use trial and error to see through it, or we can use another kind of technique. Now, we know this much, though. We know that a sub 1 is negative 1/3. Okay, good. Now, what about the ratio? The common ratio is the ratio of succeeding terms. That is, I could take something like, a sub 3 and divide by a sub 2 to find that common ratio. Let's do that here. This is, let's see, a sub 3 is negative 1/27, and a sub 2 is 1/9. So I could make this calculation, you see. Now, it's a complex fraction, and we know that it's negative 1/27 divided by 1/9, which means negative 1/27 times 9/1. Oh, happy day, we have a cancellation. The 9 and the 9, 1, 9 and the 27, 3. So we get negative 1/3 for the common ratio. So that's the way to make the calculation if we're ever confused. Okay, negative 1/3 then is the common ratio. So we can write the expression for the nth term. The nth term is first term times r to the n minus 1. And away we go to find the 8th term, a sub 8. And we have all of the information we need. Let's see, the first term from right here is 1/3. The common ratio is negative 1/3. Excuse me, the first term is negative 1/3. My bad. Common ratio is negative 1/3, and we want the n minus 1. Well, that's 8 minus 1. You see, we want the 8th term, so it would be 8 minus 1, which is 7. So we have a sub 8 then is negative 1/3 times negative 1/3 to the 7th. But if these two are alike, then I have like bases. I can add the exponents. The exponent here is understood to be 1. So we could write this as negative 1/3 to the 8th power. And there are other ways to manipulate this as well. I mean, we could pop it into the calculator right now, but just realize that there are a lot of ways to manipulate fractions raised to exponents like this. I'm noticing, first of all, that I've got an even exponent on a negative number. That's going to make this value positive. So I can eliminate the negative sign right away. I could also apply this exponent to numerator and denominator separately, and I could think of this as 1/3 to the 8th power if I wanted to. Now, it's important to realize these different manipulations because you may have an answer in the back of your textbook that is some variation on this manipulation, and you have to be able to recognize whether or not you have correct answers or not. And by the way, 3 to the 8th power is 6,561, so you might see that in this denominator. And if we wanted a decimal approximation, we could pump it into the calculator. Suppose we know that a sub 2 is 3 and a sub 5 is this fraction. We want to find a sub 1, and maybe the problem would ask to find a sub 20 or something else here. But regardless, we always start problems like this in pretty much the same way. We take this model for the nth term of a geometric sequence, and presumably we would be told that it was geometric here. But we would start with that notion. We would say, okay, the nth term is a sub 1 times r to the n minus 1, and just put in information that we know. We have information about a sub 2 being 3, but we know this. If this is a sub 2, then we have a sub 1 times r. We don't know either one of these, but n minus 1 is a correspondence here with this n. This is the n we're talking about. So if 2 is n, then this would be 2 minus 1 or simply 1. I'm not going to write the 1 here, but it's just a sub 1 times r. And we're given the information about the value of a sub 2. It's 3. So this is 3 equals a sub 1 r. That's all that we know so far about this. Now, what information do we have knowing that a sub 5 is that fraction? Well, in a similar way to this situation, if a sub 5 is 3/64, and we know a sub 5 is found by taking a sub 1 and using the common ratio as a factor 5 minus 1 or 4 times. We're given the value of a sub 5 as 3/64. And away we go. Now, away we go. Where are we going? Well, let's see. We have a couple of equations here involving a couple of unknowns, the a sub 1 and the r. So 2 equations and 2 unknowns, we ought to be able to solve this system of equations. And we can do that by just finding or solving for one letter in one equation and putting the information into the other equation. That's by substitution. So it's pretty easy here to solve for a sub 1. If I do that, I get 3 over r equals a sub 1. Notice I'm just dividing on both sides by r. All right. With this information, I pop it into the other equation. If a sub 1 is this fraction, then I have 3/64 equals this fraction times r to the 4th. Oh, good. The r's can cancel here. I've got 3/64 then. Whoops, 3/64 equals 1 factor of r cancels up here. So we have 3r to the 3rd. And now I can divide on both sides by 3. If I divide on both sides by 3, I get, well, let's come up here. Dividing over here by 3, I get 1/64. And on the right, when I divide by 3, I have r cubed. Now, using this multiple root property, I can take sort of the cube root on both sides. I find 1/4 then to be equal to r. Well, if r is 1/4, then I can find the other variable, the a sub 1, by using this information back over here. We know that a sub 1 is 3 over r. Now, I could use the information here. I could use it here. I could use it over here if I wanted to. But at any rate, I just plug that back into some form that has both variables in it. And this is pretty easy to plug into. This is 3 over, let's see, r was 1/4. Now, 3 divided by 1/4 is 3 times 4 over 1. 3 times 4 over 1, oh, that's 12. So a sub 1 is 12. Now, it turns out that this is what I was looking for. I was looking for the value of a sub 1 in this problem. If I wanted to answer other questions about this problem, then I would generate the form, you see, from the model. I would generate this form by using the value for a sub 1 in r. I would do this. I would say, okay, a sub n, I know, is a sub 1 times r to the n minus 1. And I found the value of a sub 1 to be 12. And I found the value of r to be 1/4. You see, and then using this, we can generate any term in our geometric sequence.